Hello to everyone, welcome to the first tutorial of Solar Envelope tools. This set of tools were created to help architects and designers to take into account in an easier way the minimum requirements of solar access during early stages of the design process. Actually, in this tutorial we are going to show how to create a classic solar envelope taking into account different methods. Okay, so the first thing you can see here that there are 9 components. The first one is called location data reader. If you introduce the weather file, for example Amsterdam, Netherlands, this tool gives you information, basic information about the location, such as the latitude, longitude, the UTC, and also the hourly direct normal irradiance. Okay. All right. So the second step in this tutorial is we have to generate our analyzed period of time. So in order to do that, we are going to use this tool, which is called analysis period. Analysis period, so you have to introduce the latitude, longitude, UTC, and also the annual solar radiation. Now, depending on the solar access ordinance you are working with, you can actually input different periods of time. In this case, for example, since we are going to use the analysis period defined by the European standard, so we are going to enter from February 1st until March 21st. Now the input time step, we want to generate, in this case, 2 sun positions per hour. That means number 2. We need to run this component. Okay, so we run this component and we can see here in the info output basic information about the RAM. In this case, it's not a time-consuming tool, actually. These 2 components are pretty fast because it's basic information. What are we generating? The third component, once we have the sun vectors, the day duration per period, and another basic information about the sun positions, we need to generate the selected sun vectors per window. So we have these surrounding buildings, these windows, and the idea is to calculate the solar envelope in this plot, which is in the middle of the urban zone. In order to do that, we need to know for each window how many and under which criteria we are going to select the solar vectors. In order to do that, we need to use this tool, which is the Sun Vector Selector, which is seems pretty big, but it's not that big deal. So we enter the outputs from the last component as well as the time step. Remember that this has to be the same as the introduced in this tool. Also, the dead angle, we are going to set it as 10 degrees, and also the minimum altitude. The control geometry is actually, we can select different options as a reference geometry. to select the sum vectors. In this case, we are going the default value. Let's say the most common thing is to set it as the actual buildable plot, and then this vector cell, these three options are related with the solar ordinance. In this case, since we need to establish or to define a certain minimum number of hours, sun hours per day, we need to set this option to 1. Alright, this is 1, and the vector type, it depends on the method we are using and also with the control geometry. For example, in this case we are going to use, for example, a simple one, like large incidence, large sun vertical angle. So we are going to set it as 0, and the vector sum is, in case of vector cell equal to 0, no input is required. But in this case, since this option is 1, we need to indicate the required quantity of hours per day. In this case is 1.5, but take into account that this is a list, because it's a minimum requirement. You can set minimum requirements for different periods. So since we have only one period in this case, we need to input a list of dimension 1. The context is the surrounding buildings itself, but in mesh format. So we need to convert to mesh these surrounding buildings, and we have it already. Windows need to be surfaces, and also the plot should be a closed curve. Alright, and this is the design core, which is only necessary only if the control geometry is equal to 2. We will see in the next example. Now the max height is the maximum buildable height within this plot. So we are going to set it as, for instance, a big quantity, 100 meters. And now we need to run this tool. Example is not too demanding. The tool needed almost 6 seconds to evaluate the solar vectors and the sun rays for all the windows. Actually, we can display all the select visible sun rays. For instance, look at this. All these are visible sun rays. So these sun rays are fulfilling the dead angle, the minimum altitude and solar altitude, and also they are not hit by any block, any surrounding building. But if you want to know which ones of these rays are the selected ones, these are the selected ones. So you can see the big difference between them. Okay, these are the visible, all the visible rays, and these are only the selected ones by this criteria. If you, for example, want to use another criteria, vectors type, you will have another distribution, hopefully. If this is 1, you are changing to another sorting method, which is prioritizing higher solar radiation first, for example. Well, but we have a specific tool to display all of this. It's called Sun Path Generator. This tool, we need to input some basic information about the latitude, the longitude, and also UTC, but also the sun path size. We can set it as 100 meters. The center point could be the origin or the centroid of the plot. This is the sun vector's length of the sun rays, so we can set it as 40, for example, meter. These sun vectors are those generated by the second component analysis period. This sun vector they are all the visible sun vectors, and the cell sun vector are only the selected sun vectors. And also we need to input the window, because this tool is displaying for a window that we are analyzing. Different sun rays, for instance. Okay, so we need to run this. The selected window is this one. All the sun rays are this one. We can see the difference between the all sun rays, visible sun rays, and also the selected sun rays. So we need to put here, for example, and we are going to color using different colors. For instance, for the all sun rays, we can put the blue color. For the visible sun rays, we can use the purple color, and finally we can use yellow color for this case. So all right. Yeah, and also this is an important information. This is the sun paths itself, the analemmas, and also the sun path base. We can use the color. We can use black color for this. Okay, so now we need to run the tool. We can just run the tool and see what this tool displays. These are the black, because this is shown, but now we can see all. Maybe the sun path was not big enough, so we can put it 200. So we can see all these sun vectors associated with this window. In this case, these are all sun vectors, so these are common for all the windows. But if we change, we have different selection depending if they are visible or not. For instance, I normally like to introduce here the centroid of the window itself, in order to have a sense of the obstacles and why these vectors in this zone are not visible. So we can put we can select the window, introduce, instead of the center of the plot, we can introduce now the center of the window. Alright, we run again the component, and we have now the sense, perfectly the sense, and why this song is not visible. But this tool can display also the selected some vectors. Not only these were all, but of course there are some of them that they are blocked by this surrounding building. So these are the visible ones, and from within the visible ones, the selected ones. These selected ones are different depending on the sorting method we are using. For example, we can put again 0 and to see what happened with the selected some vectors for this window specifically. So in this case, only these sun rays are selected, and they are enough. Okay, so we can now generate the solar envelope itself with the last component that are going to show you in this tutorial. And this last component is called solar envelope generator. You need to input the selected some vectors, of course, the plot itself, the grid size, which could be like, obviously the smaller value, the more time consuming this calculation will be. So I would recommend, let's put for this example 8 meters. Alright, since this actually this plot is, the dimensions of these plots are 90 meters, so let's put it 9 meters. Now the max height should be the same as introduced before. The windows, of course. And now we need to run this tool. You see, this tool was pretty simple, but at the same time, the two components that consume more time are this one and this one. Depends on obviously on the parameters, the number of windows, and the grid size. So let's run the tool. This internally is selecting each grid point, and it's checking out all the sun vectors and the intersection from each window to each grid point. So the algorithm calculates the maximum height for each grid point. That basically will allow for all the windows to receive all the selected sun vectors generated before. That's how it works. Now the consumed time was 40 seconds in this case, and the number of grid points are 121. We can just see the grid points. These are the grid points. These are the solar envelope points, so the final point. But we can display like in this form, which is not that intuitive, or at least more difficult to see. So we can use mesh the lawn image component. You can see more or less how is the shape of this solar envelope, which is better to understand visually. We can use phase boundaries as well. So we can use both, and also to preview the solar envelope itself. So you can see here how is the solar envelope. This is the maximum buildable height that will allow the fulfillment of a minimum level of solar access for all these windows. Of course, the solar envelope could be like more in a more finer grid, but also you are compromising the computational time in this case. So how is like to design with another options? For instance, we have used the actual buildable plot, but what happens if we want to clear one part of the plot so we can build more mass in around one point of the plot? We can do it also. We can do it like setting one point around which we would like to have more space here. So this is the design point, and the control geometry option will be 1 reference point. And now we can use we have to use a proper vectors type for this control geometry. In this case, for instance, we can use the some vectors not intersecting the maximum buildable volume with larger sun elevation first, and then vectors intersecting the maximum volume with farther from the design plot first. So this number 6 seems I'm pretty convinced for this method. So yeah, we can visualize not only for one window but for different windows. Now we can color all sun rays in this case. Okay, so we generate the whole sun vectors using this method. So this method will generate as a different selection of sun vectors the farther away from this point and the highest as possible. So this is the method we use, and we are going to generate again the same the same strategy, the solar envelope, to see how now the previous run was around 40 seconds. So since this is supposed to be the same number of sun vectors, this computational time shouldn't be more different than 40 seconds. 39. Well, as you can see here, there is more volume here, so the architect or the designer could even locate the let's say the core of the new building here, for instance. This is pretty useful. We can just hide the sun rays to see in detail the solar envelope and how the difference in terms of volume here in comparison with the rest of the plot, which is really flexible to play and to use in early stages of the design process. Okay, so this is the final. So we have used almost the half of the solar envelope tools. Thank you for watching, If you have any questions, you can just contact me. So in the description of this video I will put my email. So thank you for your attention, and I see you in the next tutorial.